So I think that's what we'll start with. I think we'll start with the acceleration time graph, and then after that we'll answer some questions on the homework before I throw more homework at you guys. So, because I know the next homework would be reading kinematic graphs, which honestly, there's a couple of kinematic graphs or motion maps on the homework already. So, if you see something that looks like a graph and there's motion on it, that is a motion map. Okay. I think motion maps specifically talk about displacement versus time and not necessarily velocity versus time. But when we get there on the homework, I'll try to clarify that out for us. But let's talk about, because we did displacement versus time graphs, which will tell you how far you've gone in relation to time. And then there's velocity time graphs, and the velocity time graphs will tell you how fast you're going at any particular time. So if we look at the slope of a velocity time graph, that will give us the acceleration. And if we look at the area under the curve of a velocity time graph, that will give us the total distance that was traveled. For when you take calculus, both of those have unique names. Taking the slope of that line is called the derivative, and finding the area under the curve would be the integral. So if you're in calculus, you'll kind of see these come up. For us, it's just straight lines and triangles and rectangles, so we don't have to really worry about that. Um, so let's talk about the last one, which is an acceleration time graph. And an acceleration time graph works pretty much the same way. All right, acceleration time graph. And what it does is I'm going to say that it's got the same characteristic appeal to it. So you draw two of the quadrants. So it's going to be two lines. Maybe a sideways T would be the best way to say it. And I'm just going to write acceleration on the vertical line, and we'll write time on the horizontal line. The acceleration over time graph can tell you specific pieces of information. So if you I'm just going to go ahead and just put some little tick marks here. Usually with an acceleration time graph, the lines are going to be straight or flat lines. They're not going to have any particular curve to them, because if you have a flat line on an acceleration graph, that means that, I'm going to make this part real thick to actually show that that is on the line itself right there. If you have a positive acceleration, then what you're going to get is a flat line on top. If you have a curved line on an acceleration versus time graph, that is a little hard to interpret. So like say that it's going like this. Well, what that means is if you have an acceleration time graph with something that's not a flat horizontal line, that means that your acceleration is accelerating. That means that you are speeding up, you are speeding up. So that kind of hurts my brain a lot. So fortunately for us, whenever we talk about acceleration time graphs, whenever you see them, they're going to be these nice flat lines like on the left. So we're going to get a flat line. Right, yeah. There's a name for that. It's called jerk. So like a good way to think about that is if you're driving in a car that the transmission isn't super great on, and it like you try to accelerate and it goes like and it like starts like moving. Well, what's happening is your speeding up is speeding up and slowing down. So it's not a constant rate of acceleration. So it would look, yeah. So like your acceleration time graph on a janky car would be like wiggly. It wouldn't be a straight line. It wouldn't be a flat line. I keep saying straight, but it wouldn't be a flat line. And in AP Physics, even in AP Physics, we really like these flat lines for the acceleration versus time graph. Because if we don't have those flat lines, then things start getting really difficult, and our brains start like having trouble processing. I think the English language has a little bit of a hard time processing what's actually happening there, because you're literally saying the same thing twice. Like your rate of speeding up is speeding up, and it's like what? So I don't know. It seems kind of weird. So we're just going to deal with nice flat lines. If there's a flat line below the axis, this obviously means that you have a negative acceleration. So remember though, uh, that does not necessarily mean slowing down. So just because it says that it's a negative acceleration doesn't mean that it's slowing down. A negative acceleration can indeed cause things to speed up. the Earth's negative acceleration of negative 9.8 meters per second squared speeds things up all the time. But that's because it makes them go in the negative direction. It makes them go downward. So if your negative acceleration is in the same direction as your displacement, so if you've got a negative displacement and you're accelerating in the negative direction, you are speeding up. Okay? And then the last one is no acceleration. But a lot of times people think about this. You're either standing still in this case, or you could be moving at a constant speed. Okay, so I'm going to have to put or constant speed. It is a little bit of storming going on outside right now. So I'm not really sure if it'll show up on the microphone or not. So just randomly talking about acceleration time graphs, then ominous thunder in the background. It works out perfectly. Makes it a little bit more intimidating, even though it's really not that bad. It's very dramatic, yes, for our AP Physics style going here. All right, so I'm going to show you guys a series of graphs, and these are going to be basically quick sketches. So I'm just going to make little L's, little L shapes for them, and I'm going to write distance, and I'm going to write velocity, and I'm going to write acceleration. And I'm giving you guys some scenarios and what's going to happen. So if you get a displacement versus time graph that looks like a curve, then that means that your velocity time graph is going to be a straight line. Okay, and that also means that your acceleration is going to be positive because you are speeding up, but it's going to be a flat line. Okay, so it goes from curvy line to straight line to flat line. Okay, so you're basically losing degrees of freedom because it goes from like a curve, then it goes to a line, then it goes to a flat line. So, but that's not the only cases where this can happen, because if you have a displacement versus time graph that makes a straight line, but not a curvy line, that means that your velocity is a flat line and your acceleration versus time graph is flat. It exists, but it's zero. Okay, so you basically have a flat line. So it's really hard to show with a pen. So I'm gonna make it like a green to say that it's zero. Okay, and then if you have a displacement versus time graph that is flat, that means that your velocity versus time graph is going to be zero and flat, right? And your acceleration versus time graph is also going to be zero and flat. Okay? So what kind of happens here is this is one of the ways that I try to remember how to use displacement, velocity, and acceleration graphs, is that displacement graphs are usually the only place where curving occurs. Like this is the only place where we can have a curve on a graph. Most of the other ones are going to look like straight lines. Whether or not that straight line is a diagonal, flat, or zero makes a really big difference to us. But for a displacement versus time graph, this is the only one where we're going to see a curve that goes along with it. Okay. Velocities can be either curved or, they can take this. They can take this. I'm sorry. They can take this diagonal, not curved. They can take this diagonal. They can be flat, and velocities can also be zero. Okay. If a velocity is zero, then one of two things are actually happening. You are either not moving, or you're at the turning point. Okay, so like for example, if you take something and you throw it up in the air, there'll be a point like right in the middle to where it's not really moving. It looks like it's standing still for just a brief moment, and then after that it starts to speed up again. I'm not going to throw my digital pencil because that seems like a really bad idea. Let's take this glue stick. I'll purge the glue stick later. Like whenever you throw it, you actually have it move up in the air, but at the very top, it stops and it starts to come back down. At that point in time, you would have a zero velocity. Okay. If you were to try to graph that like it was a velocity time graph, it looks very strange because if you're taking an object and you're throwing it up in the air and then it goes back down, and I ask people what a velocity time graph of it looks like, usually they give me a displacement time graph. So for my digital people who are learning from afar, here's kind of what we're talking about. You take an object, you throw it up in the air, and then that object kind of stops and then it goes back down. Okay, so at this point right here, if we were to graph the entire thing, at the top, the velocity at that point equals 0 meters per second. But if you plotted the entire velocity versus time graph, how would you graph it? We don't need specific numbers, we just need ideas. So where would we start our velocity versus time graph? Positive, negative, 0. We would start our velocity time graph at 0. Why would we start our velocity time graph at 0? When you throw a ball up in the air, it's not moving? Okay, so see, here's the thing to think about. Like, a velocity versus time graph does not have to start at 0 because at the very beginning of motion that we're interested in, that velocity is actually already moving. Okay. There is the argument that people make and say, well, at the very beginning, it's not moving because you haven't thrown it yet, right? But in AP physics or in regular physics in general, what we're really interested in is we're interested in the motion that is caused by whatever action we take. So whenever we throw the ball up in the air, what we're interested in is we're interested in the velocity right when it leaves your hand. Because when it leaves your hand, you don't have any control over it anymore. Once you throw that ball, once it leaves your fingertips, you have no more control over it. Everything that you've done for that ball has already happened. Okay? And what we're looking at is we're looking at the consequences, what happens over time of that ball. So it starts off at a positive value, then it goes to, let's say I'm just going to make a dot right here. It starts off as a positive value, and then eventually at some point in time, it goes to, it does go to negative, but it has to cross something before it goes to negative. 0, right? It has to cross a 0 at some point. So it'll reach 0, and then after that it will go into negative territory, and it will continue going down. So a velocity versus time graph of throwing something up in the air looks like this. You start off with a positive velocity, and then as you go, as it negatively accelerates, it starts to slow down, and then after it reaches the top, it will then speed up. So there's actually, like, even though it looks just like a straight line, there's a lot of information to dissect and digest here. So starting off with a positive velocity, then going to 0, and then moving down into the negative territory and speeding up. There's so many things that we could say about this. Um, First of all, if we calculate the area under the curve, what would the total distance that it traveled or the total displacement that it traveled be? I should use the word displacement, I'm sorry. So this would be what kind of shape is this if we were to find that area? Okay, and this would be what kind of shape? Is there something similar about those triangles? Yeah, so like they cover the same distance, right? So, and they have the same area. So if they have the same area, the total displacement of just throwing something up in the air and then catching it again is 0, which makes sense. The areas are going to cancel each other out. Okay, and it makes sense if you take something and throw it up in the air and then catch it again, that it ends up back in its original position. Okay. What doesn't make as much sense though is to say that, during this point right here, there is a negative acceleration, and during this point right here, the wording doesn't change. It's still a negative acceleration. Okay. Now, however, since this top part has a positive velocity, notice how those two are opposed to each other. So a positive velocity and a negative acceleration means that for this part, it's slowing down. Okay. But down on the bottom side, you have a negative velocity and you have a negative acceleration. So during this part of the graph, this is the part where it's actually speeding up. But even though I have a speed up and a slow down, the rules didn't change during the entire part of this motion. The gravity is always under effect, and that doesn't change. Okay, so if I were to look at it at any particular part, gravity is always pulling down, and that doesn't ever. There's no deviation. Okay, does that kind of make sense? All right. So I think that's all I really needed to say about the acceleration versus. Let's make an acceleration versus time graph of this really quickly. And then after that, I'll be done. I'll stop my yapping and we'll go over some homework stuff. If I were to make an acceleration versus time graph of this, what would it look like? If you say curve, you're way out in left field. Okay. Are we accelerating at any particular point in time? This would be a positive acceleration. This would be a negative acceleration. So at all points in time, there's a negative acceleration. Let's just say that this far down is 9.8. And our acceleration versus time graph of this is going to be negative, flat line all the way across. Okay. Even though we had a positive velocity at the first part, and even though we had a negative velocity at the other side, the acceleration is always going to be negative 9.8 meters per second, negative 9.8 meters per second. Always. Okay. So, like, what is the acceleration happening for this ball? Negative 9.8, negative 9.8, negative 9.8, negative 9.8, negative 9.8, all the way across. Okay. So, that's going to make it a flat line. These graphs are going to take a little bit of practice because like our brains aren't necessarily used to thinking in terms of displacement, velocity, or acceleration graphs, and things that make a whole lot of sense to us are actually not how it works on a graph. And that's one of the main reasons why the AP physics test is usually so difficult is you'll be answering questions and you think that you're doing the right thing. You're just like, "Oh yeah, I got this perfect." And then you go back and look at it and it's like, "Oh, that was really not what I wanted to put." Welcome to physics. That's generally what happens a lot, to be honest. So I don't know. Let's go back and let's look at the homework before I move on and talk more specifically about the different types of kinematic graphs, because I think the next part just has like us taking the graphs and interpreting them. We've pretty much already done everything that we can do with that. So let me go up here. I think I gave y'all position and velocity. Yeah, this guy and this guy. I think he had both of those. So, is everybody okay with like the first graph up at the top? Okay, just had to plot it. What about the mathematical model? Whenever we're writing a mathematical model, that needs to go either, I think, did this one make a straight line? Okay, if it made a straight line, then the mathematical model is y equals mx plus b. So that means you need to find out what the slope is, and you need to find out what the y-intercept is. Let's say, I'm just making this up, let's say that it did this, okay? Then your slope is going to be your rise over your run. Pick 2 points that work out really nice and find that rise over run to get your slope. That would be M. And B is going to be wherever it meets right here. If it starts at 0, 0, which it definitely looks like that is not the case, if it starts at 0, 0, then your y-intercept is going to be down at the bottom, okay? But it looks like we do have a y-intercept here. So our mathematical model is going to need that slope, and it's going to need that y-intercept that goes along to it. That'd be the mathematical model. Um, do, 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 how far from the origin? So you just measure out the parts on the graph. When it says to sketch a motion map, oh, they already have the displacement versus time graph. That would suffice to me as making the motion map if you put it on the graph up there. Okay, that would be I would consider that fair game. Let's see. The timer started a little bit later this time, and then this data was recorded. So same mathematical model. Does anybody have any questions about these? Okay. And then we had these things. These things are a little bit worse because these actually, a lot of these involve 2 dimensions. And if you said that you were okay with number 30, I don't necessarily know if I would believe you or not because 30 looked like it had a little bit of alphabet soup. Um, so let's go through these like individually. And is anybody okay or does anybody need help with number 27? You can name them whatever you want to, and that's perfectly fine by me. Just make sure that on the thing that I know which one they are. But that's basically just doing the Pythagorean theorem to get the distance between them. 28. See, looks like you're standing 1.83 meters above the ground, and you're standing away from a tree. So you're trying to measure how tall the tree is. This is uh, basically this is a trig problem. This is straight out of a trig book. So SOHCAHTOA should be okay. 30 and 30. Okay, 31. Okay. Um, 30 was fine. Wow. Okay. I'll take it. I'll definitely take it. 31. You're on a treasure hunt, and your map says walk due west for 52 paces, then walk 30 degrees north of west for 42 paces, and finally walk due north for 25 paces. What is the magnitude of the component of your displacement in the direction due north and due west? Okay, that's fair. Yeah, so like there are three places that we have to go, right? So let me show you guys a trick that goes along with this, because there are three individual parts. So I'm gonna copy this, and I'm gonna give myself some room to work so I can show you guys how this thing does its thing. Let's see, I'm gonna take number 31 if my computer can handle it. I'm gonna go whoop, and I'm gonna scroll down here, and there we go. Okay, so now I have a little bit of space to actually write this stuff down with. All right, and it says walk due west for 52 paces. So we're going to walk this way, 52, right? Then it says we're going to walk 30 degrees north of west for 42 paces. So I'm going to make a different arrow that goes 42. That was supposed to be green, but whatever. 42, and this angle is going to be 30 degrees, right? Okay. And then last, we have to walk due north for 25 paces. So we're going to walk this way, and that number is 25. Okay. So what we're going to need to find is it makes the easiest way to deal with this is it basically makes a gigantic right triangle. Okay. So the way that I'm going to figure it out is we have an endpoint here. I keep trying to change this, and it's like, no, come on. Ah, I didn't want to change. Okay, fine. Whatever. Start trying to take pictures of things, and it's like, no, everything is blue. Here we go. So this basically is going to make one very large triangle. But the deal is that we know some of the sizes, but we don't know this part of the triangle right here. We're gonna and basically that makes an even smaller triangle, and we're gonna have to use SOHCAHTOA to figure it out. Okay. So there are a couple of things that we can do. My favorite way to do it is to just go ahead and break this bottom one down into horizontal and vertical components. So I'm going to take this specific spot right here. Of course, I'm not able to change it. I'm going to take this specific spot with the 42, and I'm going to see if I can actually get it to change with the mouse. Nope, it just hates me. Okay, well, we'll just deal with it. We're going to take this guy, and I'm just going to write it out over here to make a longer triangle. This is 42. This is 30 degrees, which means using SOHCAHTOA, we can find the other two sides. And once we do that, we'll have the two magnitudes of the displacement. So we have the hypotenuse. So we can use the sine, and I can say the sine of 30 degrees is equal to the opposite side over the hypotenuse, which is 42, which means the opposite side is going to be 42 sine 30, which I believe that answer is 21. Because if you type in sine of 30 in your calculator, I'm pretty sure sine of 30 gives you 1/2. So it's going to be 21 here. Okay. And for the other one, we have to use the adjacent side, so we're going to use the cosine. I'm going to try to avoid using 21 just in case I messed up. So if I messed up on the sine and I type that in for the cosine, it's going to mess up as well. And I'd rather be half right than completely wrong. So I'm going to keep using this 42. So to do that, I'm going to use the cosine. Say the cosine of 30 degrees is equal to the adjacent, which is the side next to it, the horizontal side, divided by the hypotenuse, which is 42. So that means our adjacent side is going to be equal to 42 cosine 30. That one is not a pretty number. So the adjacent side, it's okay. Decimal is okay, but if you write 3 radical 21, that's fine too. Um, that is correct. It would be 3 radical 21. Um, I think. Are you, well, uh, is it the square root of 3 over 2? Okay. How does that come out to 3 radical 21? I might need to work that one out. What I normally do is I just put this in the calculator and it gives me a decimal. And then that decimal, that's what I go with. So, yeah, yeah, and it is. It's radical 3 over 2. And you can easily get it to work out that way. However, whenever you're dealing with these like paces and stuff like that, I'm just going to add them all together. So I'm going to type in like 42 times the cosine of 30. What's that as a decimal? See if I can get it before y'all do. 42 cosine 30. Oh, I got it. But do y'all got it? It's always nice whenever technology doesn't work. This is also a really good way to make sure that you're actually not in radian mode and that you're in degree mode, because if you get the same number as me, then we're all on the same page. If you do not get the same number of me, we are not on the same page. So type in 42 cosine 30 in a calculator for a decimal and see what it gets. We'll just go to the nearest tens place. We don't got to go crazy. 36 point what? 36 point, let's just go tens place, 36.4. So I'm going to say that this is 36.4. Okay, well then we can do everything that we need to. The horizontal component is 52 and 36.4. So if we add those two together, that's going to get us the due west component. So B is just going to be whatever 52 plus 36.4 is. And the north is going to be 21 plus 25. So this is 21, this is 25. The north component is going to be both of these added together. Okay, so whenever you do this, it just basically makes one big triangle. The cool thing about it is that works for not only displacements, but that works for velocities and forces and momentums and everything else. So if you have a bunch of different forces acting on an object, you can basically just put it into one big triangle and it works out. And that's one of the main reasons why we're doing these kind of problems, is because you kind of need to get used to in your head taking these different forces and putting them together into one so that you can make a big triangle out of it. Okay. And if you always put the head of one of the arrows next to the tail of the next one, so you go head to tail and then head to tail, it'll always come out to be a right triangle. Okay. If you put tail to tail or head to head, your numbers are not going to come out correctly. Okay. So it's always got to be tail to head, tail to head, tail to head. Okay. Make sense? If you did this backwards and you did the north first and then the other one, you would still get the same displacement vector. So it would do the same thing, except it would be a negative number because you'd be going backwards. Okay, in this case, we just all considered them positive numbers. We didn't worry about, since we were going to the left, that counted as a negative, because the direction was taken care of by saying west and north instead of positive and negative. Okay, but you could just as easily use the Cartesian coordinate system and say that, you're going vertically, you're going positive, but west you're going negative. You could have done that too, and it would work, crazily enough. Okay. What else we got here? Do y'all want to do 29, or do y'all want to do 30, or are y'all okay? It is alphabet soup. 32. Okay. It is plug and chug as well too. Okay, so I'll do 32. Um, Displacement vector A points due east and has a magnitude of 2 kilometers. Displacement vector B points due north and has a magnitude of 37.5 or 3.75 kilometers. Displacement vector C points due west and has a magnitude of 2.5, and D has due south and it has a magnitude of 3. find the magnitude of the resultant vector A and B and C and D put together. So if we find the total displacement, how far we actually went, that's what it's asking for. So best thing to do is to just go ahead and draw a picture. East is to the right, so I'm going to go ahead and start with A being to the east. And it looks like we're going east and then north and then west and then south. So it looks like we're kind of almost making a square. So to the east, we're going to go for part A. It's going to be 2 kilometers this way. Then the north is going to be 3.75, a little bit longer. Okay, and then for the next one is west at 2.5, so it's a little bit longer. These are totally not to scale, and I'm just trying not to hit myself in the process. Um, let's see here. The last one is south, and it's 3. Okay, so, oops, that won't work. It's got to be shorter than 3.75. So it looks like we're kind of end up over here. And our angles, so here's where we start, and here's where we end. Our angles are not going to be accurately represented by what we have here. But I think that 2 is shorter than 2.5, and 3 is shorter than 3.75. So at least we're going to be in the right ballpark of where we started. So to find this resultant vector, what we have to do is we have to basically take this displacement part, this part right here, and we're going to turn this into a right triangle. Okay, so between 3 kilometers going south and 3.75 kilometers going north, what's the difference between those two? Is that a positive or a negative displacement? We have a total 0.75 positive displacement for that triangle, right? Now, between 2 kilometers and 2.5 kilometers, we have a deficit because this is going to be in the negative direction. We're going to the east. I'm sorry, we're going to the west. That's going to be negative. So that's going to be a deficit of 0.5, okay? Because 2.5 and 2, the difference is 0.5, and it's an extra distance, so we're going to the left. Now, Pythagorean theorem, and that gives us the resultant vector, and then we can take those two sides and get the angle for it, and we'll be okay. So I'm just going to make this a bigger triangle, and I'm going to say we have 0.75 here, we have 0.5 here, and this is going to be c squared. So it's going to be 0.75 squared plus 0.5 squared equals c squared, and you can do math for that. To find the angle here, that's going to be the tangent of, let's just call that theta because that's the only angle thing that you guys use often. Tangent of theta is going to be the opposite, 0.75, over the adjacent, which is 0.5. And then to actually find out what that angle is, you have to use the inverse tangent button. So in the calculator, you're going to type in tan to the negative 1 of 0.75 over 0.5, and theoretically that gives us a number. Okay, does anybody have any numbers for that? Because I don't know what those are off the top of my head. Okay, so this is going to be 0.9 kilometers, which makes sense if you look at it. It's not quite going to be a whole kilometer, but a little bit less. And then to do the angle between them, 56.3. I'm going to need a second on that. 56.3 degrees. Second? Okay, so then we're going to say 56.3 degrees and we're going to be okay on that one, which seems reasonable. Now, that's going to be 56.3 degrees in what direction? Because that could be, 56.3 degrees this way. That could be 53.3 degrees this way. Okay, north of west. Okay, north of west. There we go. Now we have to make sure that we say north of west and not just northwest because northwest specifically talks about 45 degrees, like right smack dab in the middle. So if you say northwest, you're talking about 45 degrees north of west. So we have to say 56.3 degrees north of west because we're not really talking about northwest. We're talking about starting at the west position and then going 56.3 degrees up that direction. Okay? Cool. Do y'all have any other questions, comments, concerns? I think the next part is going to be reading kinematic graphs. So I think we're okay. Oh, wait, hang on. Kinematic. That's us. So the next one will involve, if I can actually get it to do it. I started taking pictures and it just hates me now. It's like, it's literally saying no. It's like, no, Mr. Broadway, you've done enough today. Time to go home. Let's try. Let's just do a reboot and see if it actually works. Reading? Ah, there you go. So basically, it's just going to be a bunch of different graphs, and you're going to have to take some of the graphs and you're going to have to make displacement versus time graphs and acceleration versus time graphs from that information. So we can spend the last 10 minutes trying to practice that concept if you want to. On some of these, there's going to be some curves involved. This is a distance versus time graph, so if there's curving, that means that there's acceleration involved. Um, well, I mean, like, it's not that bad. Like, curves for acceleration isn't that bad. It just really kind of depends on what kind of curve. You notice how all of these look like this is part of a parabola, and this part down here looks like it's part of a parabola. Um, since you've got just a parabola, that means that you're going to have a constant acceleration going there. So, yeah, I do know that those things are actually either accelerating positively or negatively, and what direction they're actually going makes a difference. Okay, so like obviously those two curves are different, which means there's going to be two different accelerations that happen there. So I don't know. We'll kind of see how that works out. See how y'all play it out with that one. Okay. And then from there, I think that's just analyzing the graph. And there's another example of velocity versus time graphs. And then I think from there, that's pretty much it. So I don't know. I guess let's talk about dealing with like a velocity versus time graph and taking that velocity versus time graph and turning it into a displacement versus time graph. So tell me, in this section, what's happening from 0 to about 8 seconds? What is decreasing? The velocity? Okay. So is the acceleration slowing down or is something else slowing down? Okay, so like the velocity is getting more negative, right? The velocity is constantly going down. So since we see that that is a constant rate of change, the acceleration during this entire time is constant, not zero, constant. Okay, and I know that it's constant because at the very beginning, I was going 4, then 3, then 2, then 1, then 0. In order for you to change speed, you have to have an acceleration. It can't be 0. Okay? You can have a velocity be constant and have 0 acceleration, but this is not a constant velocity. This is a changing velocity. Okay? On the bottom part down here, this velocity is not changing. So since this velocity is not changing, that means that we have an acceleration of 0. There is no acceleration happening there. Okay? Over here, we have what kind of acceleration? Positive acceleration. Here we have a 0 acceleration. Here we have, okay. So thinking back to the curves that we had for the displacement graph, what is it going to look like up here? Flat line, straight line, or curve? Okay, there's definitely going to be some curves that happen here, right? Okay, then what about here? Straight line, not flat, straight line, right? Okay, what about here? Curve, what about here? And flat. Okay, because the velocity is actually going to be 0 for this part. So since the velocity is 0, that actually will flatline. Okay, because this is basically what this is telling you is this is telling you the slope of the line at any particular point. So from 16 seconds to 20 seconds, you are actually legit dealing with a flat line. That means that you have stopped, your velocity is 0, and your displacement will not be changing. Okay, even though these are flat lines from 8 to 15 or 16, no, sorry, 8 to what is that? 9, 10, 10, 11, 12, 13, 12. From 8 to 12, even though this is a flat line, you are still covering a distance. And you are still doing some kind of distance over time because you have a velocity. And then from this part right here, you have a positive velocity and it's not moving up, so there's going to be no curve here. This is going to be a straight line. Okay? Yeah. Negative slope does mean negative acceleration. Yes. So I would say that from this entire point, from 0 to 8, you have a constant negative acceleration. Okay, which means on the acceleration time graph, it's going to be below 0. It's not going to be above 0. It's going to be below 0. Okay. One of the things that I normally do is I have us make displacement time graphs with our bodies. So like we will actually have a set of instructions to where we move a particular distance, and I will probably be videotaping you guys this time because I need uh, I need stuff for the digital people to be able to use. So I'm going to give y'all a set of instructions tomorrow, and I'm going to videotape y'all, and we're going to like literally move around the room and make our own displacement time graphs, velocity time graphs, and acceleration time graphs. Okay, which means that whenever we do acceleration time graphs, we need to learn how to hustle. Because what happens a lot of times is people will accelerate for like half a second, and then they're like, okay, I'm good. Okay, because after you reach a certain point, it actually doesn't take us very long for us to like start running, and then we've reached our constant speed. Like we can't really go any faster. So like we have to be really careful about how we slow to speed up. We have to speed up. I said slow up. We have to speed up at a very slow rate because if we don't speed up slowly, you're just going to reach your max speed and then that's going to be it. Okay? It's like think about how long it takes you to accelerate to start walking. Like a tenth or a quarter of a second, and then you're already at your speed. You're like good to go. Okay? It doesn't take very, very long at all. So we got to be careful about that, but it'll be fun to do. At least we can do velocity versus time graph and play around with that. Do y'all have any questions? Do you want me to unlock the next homework, or do you want me to wait until tomorrow? Okay, I can deal with that. I can do that because I gave y'all two at a time last time, so I can wait until tomorrow to unlock that assignment. So I'm sure the digital people will agree with you guys completely. So I'm going to leave it be, and I don't think we have a whole lot of time left. 11:06, we get out in about 2 minutes. So I'm going to go ahead and stop it there.